Hello and welcome to Toddcast number 64. We're zipping along through the carbonyl chemistry. And what we're going to do in this lecture is going to cover very common reactions in both OChem and biology, and that would be hydrolysis, using water to break a sigma bond or a pi bond, possibly both. And then we're also going to do dehydration reactions. And specifically, we're going to do imine formation, where a ketone or an aldehyde can be converted into an imine, which is a carbon double bonded to nitrogen. And so we'll look at the mechanisms, but most importantly, we'll look at a pretty powerful shortcut for quickly determining what occurs in a hydrolysis reaction or uh, I'm going to say elimination for lack of a better word, but dehydration reaction that is usually along the lines of elimination. So, uh, with no further ado, I want to get into something called the magic water line, and I'm going to tap the name onto it. So, way back when, we're talking way back when, 1989, first time taught full-fledged organic chemistry, introduced this concept, and it just worked well. So I stuck with it for a lot of years. It is the magic water line. If you draw the line the right way through the bond broken and put the OH and the H on the correct side, ta-da, you get the product. Nothing really exorbitantly brilliant about it. It's just common sense observation over and over. So here's how it's going to work. We're going to carry out the hydrolysis of this ester. So, ooh, it's ester, two O's. Going to add water to it. We're going to break the bond that leads to the leaving group, but ends up being this sigma bond right here. So you have to know the reactivity that happens, but we're only going to break one bond in this case. So I'm going to draw a line through the bond I'm going to break, and I'm going to add an H and an OH. That's going to be the sum of what water goes. And so the important thing is recognizing where they go. So there's the line through the bond broken. The carbon is going to get the heteroatom. The heteroatom is going to get the H. So OH goes to the carbon, H goes to whatever the leaving group is. This is really typical of what we see. I mean, this is going to be repeated so many times over and over. So in the end, you add an OH to the carbon and H to the OR. So you end up with an OH. So this OH right here is this one. And this H right here is that one on the OR. So note the OH and the OH. And the H on the OR and the H on the OR. Fairly straightforward. So we'll try again. This time, instead of a ester, we have a compound known as an amide, carbonyl with a acetyl bond to N. Hydrolysis of amide, a little bit harder to pull off, but can still be done. It's just not quite as good a leaving group. But so we're going to break one bond. And in breaking one bond, we need one water. And well, we need one water bond broken as well. So OH and H will be the resulting two fragments. Going to draw a line through the bond broken, just like we did before. Going to add an OH to the side with carbon, add an H to the other side, and voila, you have it. So in the end, you have, once again, the OH on the carbonyl and the H on the leaving group. So again, fairly straightforward. Okay, so what if it's not one bond you're breaking? What if it's two bonds you're breaking? So if I'm breaking two bonds from carbon to some other atom, then I need to break two bonds in water. Well, ends up there's only two bonds in it. So you end up taking both bonds of water and breaking into an O and two individual H's. Same rules as before. Draw a line through and then place your atoms accordingly. O, just like before, was an OH, but now it's just the O goes to the carbon. Remaining two H's go to the leaving group, in this case, nitrogen. So O next to carbon, two H's here, the magic water line. So this becomes a molecule. Actually, I should say color coordinate. So that should become a molecule, and that'll be a molecule. And sure enough, that's what we get. We get the bottom portion bonded to an O, get the top portion, nitrogen bonded to two H's. The magic water line works beautifully. Okay, just double check. That O is here, those two H's are there, that OH is there on the carbonyl, that H works beautifully. So if you have one bond, you only break one bond in OOH, so you get an OH and an H. If you have two bonds that you're breaking, then you need to break two bonds in water, so an H and an O, and well, HO and an H. So let's do one more of those. The two bonds don't necessarily have to be between the same two atoms. It can be between carbon and one O and carbon and another O. So hydrolysis of an acetal or a ketal, two bonds. So I need to break two bonds here, two single bonds here. So I'm going to need to break water twice, water bonds twice. So OH bonds, both of them get broken. You get left with an O, an H, and an H. Going to draw the line and going to put the H's with the heteroatoms and the O on the carbon. So once again, we're going to have a carbonyl on one side and the leaving groups that have been protonated on the other side. So this O is connected to here, that's your carbonyl, and you end up with two acids, two alcohols, excuse me. My apologies. So your H's, your two H's are here, there's two of them, and your O is here. Okay, so one bond, no problem, two bonds, no problem. Three bonds is what messes with people. For three bond hydrolysis, there's only two bonds in water, so you need to take on a second water. So let's figure out what we're going to do. We have an H, an O, and an H. So if I'm going to break three bonds, then I need to break one, two, oh shoot. I need to break three bonds. So altogether, I'm going to have one, two, three individual H's, an O, and an OH. So for three bonds, you will get an OH, an O, and one, two, three H's. As always, O's go to the carbon. So you have a single O and two H's going to carbon. All three H's go to the leaving group. So I get H, H, and H here. So from the H to O, H2O, notice that water bond has been broken twice as well, one there, and then the OH and the H. So perfect. So the carbon is going to get a double bond to O and a single bond to OH. The nitrogen's going to get three hydrogens. So I make it NH4 plus because that's ultimately the state it's going to be in because it's acidic conditions, but only three of the H's are the ones that got through hydrolysis. So it has the O here, the OH from there, one, two, three H's are here, one, two, three. So fairly straightforward chemistry. So the magic water line will make life much easier. So quick summary, decide what is breaking. Is it one bond, two bonds, or three bonds? However many bonds are breaking in the compound, you have to break the exact same number of bonds in water. So you break one in the compound, you break one in water, and you end up with an H and an OH. You break two in the compound, you need to break two in water, so you break both OH bonds and results in an O and two H's. If you break three bonds, that rare case with like the cyano group we just showed, you have to break three bonds in water. Water only has two, so you have to break two waters up. One of them into an HO and an H, and the other one into an OH and an H. So it's fairly straightforward. Just practice with it, and it should work out well. So I want to consider this for a more complex molecule. So we're going to talk about a glycosidic linkage, which is nothing more than, say, a fancy acetal or hemiacetal linkage between two sugars. So glycosidic simply means between a sugar and some side chain, which for polysaccharides, disaccharides is another sugar. So here we have one sugar, this would be lactose. The other one we have glucose. This is lactose for what it's worth. I have a carbon here that has two bonds to O and an H coming down. So that would be an acetal. But I also on the other end have a carbon here with an H coming down that has an O and an OH and an O and an OR. So this is a hemi acetal. Okay, so hydrolysis glycosidic linkage is going to convert this right here. So your leaving group right there. So if I'm breaking one bond in the molecule, which I am, then I need to break one bond within water. So HO and H, meaning the OH is going to go here. H is going to go on the heteroatom. Okay, let me erase all of my writing. Hopefully this lead-in makes sense. There's the bond you're breaking, and again, OH, you're breaking one bond in the compound, so you have to break one bond in water. OH stays with carbon, H goes with the OH. They spread out, and ta-da, there you have it. You have your results from the magic water line. You have galactose as one sugar, and you have glucose as the other sugar. So oxidation is not hydrolysis. Hydrolysis is not oxidation. You're simply adding water across a sigma or pi bond. You are not converting an ester into an acid. You are converting an acetal into a hemiacetal. You are protecting a ketone? Not exactly. Protecting a ketone would be adding something to a ketone to turn it into a ketal. You're unprotecting a ketal? Kind of. That's going to be the closest thing we can say. So water's a reactant. So not a product. So I'm protecting a ketal, although technically I'm actually unprotecting an acetal. So good way to look at it. So far, so good. So we will continue down this path. Going to look more at instead of hydrolysis, going to look at the opposite. So as much as I like the plan of going here, H, H, and O, because I'm breaking two bonds, so break two bonds in water. That's your carbonyl right here. Here are your two H's there. So that's a reverse. So hydrolysis breaks that, but to go in the forward direction, you do the exact opposite. Instead of drawing a line and adding the water across, find the water and get rid of it. So going to draw these two in a way where the O, which I drew in that previous example, the magic water line, and the two H's, I want them to line up in a way where I can see them close to each other. So there's water. So we break with a magic water line, we rebuild with a magic water box. So we have a magic water box the H, and the O, have these come together to form water. So we move to the water and connect the atoms. So H, and O are gone. So there used to be two bonds of this carbon to O. There used to be two H to here. So we just make a double bond there. So your final product is benzene ring connected to what used to be the aldehyde carbon, which is now the imine carbon, double bonded to nitrogen, and a CH3 coming off of it. Fairly straightforward, not so bad. So as opposed to the magic water line, which breaks, this is the magic water box. Box your water, get rid of it, plate connect the atoms. Okay, so we have the magic water line and magic water box for quickly analyzing reactions, but we also need to know the mechanism. So as always, we're probably looking at a protonate break make deprotonate if we do it in acid, or a deprotonate make break protonate if we do it in base. So going to do this in acidic conditions. So HA, some acid, and this time I'm going to make it a positively charged system. So the H, when those electrons go back, the H is going to have a positive. So the A is now neutral, it's happy, and carbonyl has been protonated. So protonate, next thing you're going to have to do is break and make. So you're going to break that bond and make that bond. So leaving group will first leave because it's a cation, so it's going to be more SN1-like, even though it's SN1 because I'm dealing with an sp2 carbon. But I like to just think of it that way. SN1 has to be sp3, but either way, if I have a positive, I typically break before I make. So protonate, break, make. This compound, so you need to deprotonate it. So A is going to come back in, pick up an H, and you have your compound. Or do you? So unfortunately, as we often find out, one round is not enough. Protonate, break, make, deprotonate. Didn't do it, so I got to take that same compound, start all over again. Protonate the OH, because that's what I want to lose. So protonate, break, and then the carbocation is going to be stabilized by resonance, which would be make. And last but not least, deprotonate. So the water is going to come in, or the A is going to come in and pull it off. So actually, let me color coordinate this. Not sure what happened to that arrow, but we have the deprotonate step. So there we go. Not too shabby of a mechanism. Protonate, break, make, deprotonate. Okay, so want to do a slight variation on this one. And the variation is instead of an amine, it's known as a hydroxyamine. And you're going to end up with oxime as a product. So just going to behave the same way. You still have to simply identify O and two H's are making water. So the result will be an N with an OH instead of like before we had N with the CH3. So same thing, find your magic water box, get rid of it, connect the two atoms, and end up with that compound. Fairly straightforward. Hopefully you take to this. So again, known as an oxime. So we used a hydroxyamine and we generated an oxime. Okay, so let's see what happens in this case. So somehow, some way, I believe I might have drawn an incorrect compound. And so what I meant to draw and should have drawn here is, let me just erase this all together. And we end up with an N and NH2. So something known as hydrazine. So hydrazine is this compound right here, two NH2 stuck together. It's still going to be the same story. The water is going to be dismissed, and you'll end up with connect the dots. Let me erase those. You're now in the wrong place. Now with the compound you want. Same type of reaction over and over and over. Just whatever's connected to the N, so it be it. So first one I did NH2 with a CH3, then second one NH2 with an OH, third one with NH2 and an NH2. And you have a dangling NH2, a dangling OH, and the previous one you had a dangling CH3. So let me give you the name of this. This is known as a hydrazine. And the product is known as a hydrazone. So hydrazone is a type of compound, hydrazine is the reactant. So far, so good. So secondary amines are amines are going to introduce a cool little synthetic trick, but they're going to be kind of a pain in the butt for us. So same sort of thing, going to protonate, just like before. So protonate. This compound then is now going to have a break, where you break the pi bond, and a make, where the amine is going to attack in, and then a deprotonate step to get rid of the positive. Looks awfully familiar because I basically cut and paste the same thing. I was kind of lazy. But here's where we run into some problems. As it were, I can't do another deprotonate like I did on the last one. So I can protonate the O, that's fine. So protonate, and then it can leave. I can deprotonate, or not deprotonate, excuse me. It can break, and it can make. But now the last D, instead of standing for deprotonate, stands for damn. Not sure what to do. I cannot deprotonate where I normally expect. I can't deprotonate off the N. So it ends up, I have to steal an H here. So it has a base has to come in down there, take it off, and then that has to flow up into here. So in the end, your deprotonation is in a different location. And the water in there just was a tease. Didn't necessarily have to be in there. So this one is called an enamine. So an enamine. So imines versus enamines. If you have a primary amine, then you're going to end up with an imine compound because you have two H's to lose. H2 and an O. If you only have one H, then you run into issues. Now you have to take one of the H's from that compound, but you have to take one of the H's from here, from the alpha protons. And it could have been on either side. It could have had it here or here. So just something to keep in mind that with a secondary, you end up with an enamine. So secondary, you get an enamine. Primary, you get just your run-of-the-mill imine. I'll redraw that circle a little bit because that primary is not as pretty as, oh, that's so much prettier. Secondary enamine utility and synthesis. So here's one of those cool little reactions you can do. A fairly complex molecule, a lot of carbonyls going on. If I add a molecule known as proline, so proline is a secondary amino acid. And so the key thing is it's secondary nitrogen. So when I add it, it ends up adding in a way where, because it's secondary, we get an enamine. So there's my ene, there's my amine. So this compound has a chiral center, which has an influence that impacts the rest of the structure. So if I had a base, I'm going to end up, in this case, let's trace where the heck the various atoms have gone. So if I trace this out, looks like there's my ring, got that, there's that group coming up. The CH3 must be interesting where it's coming in. And I need to figure out what became of this N. So this is, and since this is where you need to number carbon. So 1, 2, 3, 4. 1, 2, 3, 4. So this must be, actually, let me choose a color, better color. This, sorry. This must be that. And then this concoction, if you remember, we were able to turn a carbonyl into an imine, or an enamine in this case, and then turn it back to a carbonyl. So this right here is this right here, which ends up being that one right there. So crazy as this is, this carbon-carbon bond had to attack right there, kicking that up to form an OH. So the enamine can hold it in place so that this can be a nucleophilic carbon to attack and close a ring. Utter craziness. TSOH puts a tosyl group on there, which will help us clean up this mess. So basically, we can turn this into an OTOS, and then we can do elimination and get an alpha beta unsaturated ketone, as it's called. So the whole cool utility of this is that one can help get certain specific chirality, which ends up being a moot point because we lost it anyway here. So sometimes you choose a chiral compound to influence the chirality down the road. But more importantly, instead of having like the random reactivity, we have very specific enamine reactivity to close the ring. So hopefully that makes sense why we care about it, but you'll see it as something very common in some of these processes. So this reaction is known as the Whelan-Meischer ketone. This is a synthetic precursor to so many things that we end up building. So I don't know if you recognize, but this is the start of let's say, a steroid, so an androstenedione ring system. I had a couple more rings, a 6-member, 5-member ring. I'm on my way, and I have the functional groups where I need them there. It also is a foundation of a bunch of other molecules. But this is how you generate one. And enamine chemistry is a lot cleaner, a lot higher yield. Hopefully this seems okay. Hydrolysis of enamines and amines. So if we can form them with the magic water box, We can break them. The magic water line, nice and easy for imines. H, H, and O. So you end up getting that compound. But uh, when you have a secondary, so a secondary one goes on to form the enamine, that's where it's a little bit trickier. So you are breaking two bonds, one here and one here. So you're going to end up with an H, an H, and an O. So again, if you're breaking two bonds, which we are, then you need to break two bonds in water, H, H, and O. You're breaking two bonds, but one here and one here. That's where this is utterly crazy. So H and OH, if you do it one time, and then becomes an enol, and enols turn into ketones. They tautomerize. So you can draw it this way if you want. Do two at one time, or you do one at a time. H and OH break one bond, and then figure out what it turns into. A lot going on there. This was an impacted pool of information. Okay, so one last group of compounds, thioacetyls. Much like we did alcohols, just want to point out ROH turned this into two OHs, or ORs, excuse me. SH just turns it into this. And in and of itself, this may not seem useful, but sulfur chemistry has a lot of synthetic purpose. So we can, in one direction, we can do like just break it into, in this case, instead of water, it's S's. So H, H, SR, SR. And then to go in the other direction, get rid of your water, and you get that compound. So you can do it in whichever way. So that, I mean, either way you want to look at it, you're going to end up with this situation. So magic water line, or get rid of the water in the box and play connect the lines. Both methods work. Okay, so that's your compound. And again, same story. Find your water and see what forms. So line your water up, magic water box. I'll do that one. Get rid of the water and form the sulfur compound. This one's going to become important not as a protecting group, but as something that facilitates a reductive process of a ketone. We'll get into that in a very short time, but just a little foreshadowing for it. If you had something called rainy nickel, which is just nickel with, I guess, very specific impurities that ends up in the presence of hydrogen source, we'll add H's across here. So you end up with an H on the carbon, H on the S, H on the carbon, H on the S. So you end up reducing overall a ketone into an alkane. So if you want to get rid of a carbonyl group, you can. Okay, this was impacted. There was a lot of stuff. It kept on going and going and going. The big things you need to hang on to: magic water box, magic water line, and then primary amines go to imines, secondary amines or amines go to the, I guess, the intermediate uh, cation, which eventually becomes the enamine. Hopefully it seems okay. Lots to study, but for now, we'll call it a Toddcast. Thanks for joining in, and I will see you at the next Toddcast. Bye.